All right, this is Computer Science 305, Programming Languages. Today we're going to be talking about types. So a type is a set, right? So whenever we declare a variable that has a certain type, what we are saying is that the value the variable can have are elements of a certain set, right? And so if a type is a set of values, it also has so a type is a set of values with an underlying low-level representation, right? Typically, we can represent everything in some form of binary or hexadecimal, or however that it's supposed to be represented inside of memory, and so that the machine can actually understand it. Along with this low-level representation, there's also a set of operations that can be applied to the potential values that are representing this set of values. And so today what we're going to do is we're going to look at a tour of types, right? In reality, across all languages that have ever been developed, and all the type systems that are part of those languages, it would be impossible for us to even cover more than a handful of what's out there. But instead, what we would like to know is being able to understand how these things are constructed, what they really are, and so that we can actually understand them and to apply what we would say is a set of rigorous mathematics to understand the types in any one programming language. And so essentially what we're going to try to do is connect math and essentially it's abstract type theory to the types that we can find in typical programming languages. So the outline for today, for this lecture, is basically there's a menagerie of types, which are basically broken down into primitive types or constructed types. And then we also have to take a look at the uses for types, which includes type annotations and type inference, which are part of type checking and type equivalence issues, which thus makes programming a useful thing to do. So primitive versus constructed types, right? So any type that a program can use but cannot define for itself is a primitive type in the language. For example, we can think of, we'll actually look at that in a second here. So any type that a program can define for itself using primitive types or other constructed types is itself a constructed type. So if we think about this, right, primitive types in ML are like int, real, and char. Meaning that no ML program, then an ML program cannot define a type named int that works in the same way that the predefined int does. In other words, I can define a new int, I can have it act the same as int, but I cannot define it in the same way as and make it work in the same way as the predefined int, because the predefined int is built into the actual underlying language implementation and has faster operations than what we would find with one that we make. Another way to think about this is if you think of Java, we take a look at the primitive types there, like boolean, int, char, double, all these other, and long and short and byte. You have all these different primitives, and then we have object representations of those as well that were defined or constructed within the language. But they do not operate as efficiently nor as effectively as their primitive forms, but they are necessary to handle some of the other object-oriented stuff. But anyway, those are constructed versus the primitive types in Java, right? So we also can take a look at a constructed type, right? For example, in ML, we can create an int list, which is really just a type constructed using the primitive type int and the list type constructor. So primitive types are really come from the definition of a language. It says what these primitive types are, right? It defines the specification for these types, as well as any other operations that apply to them. Some languages define the primitive types more strictly than others, right? Some define them primitive types exactly as in Java. For example, I know the size of an integer in Java regardless of the system in which I'm operating on, whether it's 64-bit or 32-bit. I know the minimum and maximum, or I can know the minimum and maximum values for an integer. That is defined as a part of the language. Cannot deviate from that and still be called Java. So, but there are other languages that have wiggle room, right? The primitive types may be different sets and different implementations. For example, in C, we go back to int and look at that, and it depends upon the architecture in which you're operating and the implementation of the architecture and operating system and the implementation of that version of C. And ML has the same thing going on with some of its primitives. So it depends on the language that we're talking about. So we want to, and this is exactly what we were talking about. So we want to compare integral types, right? So in C we have char, unsigned char, short int, unsigned short int, unsigned int, long int, unsigned long int. There's no standard implementations. But longer sizes must provide at least as much range as the shorter sizes. On the other hand, in Java we have byte, char, short, int, and long, which are exactly specified in the same order to be 1 byte signed, 2 byte signed, 2 byte signed, 4 byte signed, 8 byte signed. And then furthermore, in Scheme we have integers, which are just an unbounded range. They're integers of unbounded range, so effectively infinite, right? And these are just all primitives in different languages that have different ways of looking at this concept. So some of these issues. What sets do the question becomes, what sets do these primitive types signify? How much is part of the language specification? How much is left to implementation, right? It's almost as if we want to say that there's some sort of range in which we're operating, right? If we make it, we can make it very restrictive. It's a part of the exact specification for these types is part of the language specification itself. Implementers have no choice in the matter, or we can have it a little more wiggle room, more flexibility to target the language towards different potential underlying platforms. For example, how C works, and so it's a trade-off scenario. So that leads to, if necessary, how can if we do have a language where we have this potential for flexibility, we have to provide a method by which we can find the ranges for these different values. For example, in C, there is a I can't remember what it is off the top of my head, but there is a header file that we can include that gives us the capability to ask what is int underscore max, right, or int underscore min. Similarly, in ML, I can say int.maxint, and that will tell me what the maximum value for an integer is. Furthermore, we want to know what operations are supported, right? Typically, we have detailed definitions for rounding and exceptions associated with these different types. Other things that, and a whole slew of other issues surrounding them. Not all languages provide these things. Some do. Then finally, it's the choice of the underlying representation. For example, in floating point numbers, this is a serious consideration, right? Which has actually plagued a significant amount of both banking and scientific software when languages choose to use the IEEE standard for floating point numbers, which are based on binary as an underlying representation, and that means there are issues when you're trying with precision. When you have a large number of digits, it tends to be that you lose a significant amount of precision no matter how large the size, the maximum size of the number can be. But there are, and that's if we use IEEE floating point standard, which I suggest you go look up in your spare time, because it's the basis in both Java, I think C#, C, C++, and a few other languages. It's actually a very poor way of doing it. But if you look in, there's several languages that get around that by not using that representation, and they use, I'm not actually sure, I think they use maybe a string as the back end, or something similar to that to allow them. Python, for instance, has much better handling of floating point numbers. This brings us to constructed types. So constructed types are essentially any additional type we can define using the language itself. So these can be ones that are provided to you as part of the base library. For example, all the type in Java has a significant, very large. I think last time I looked at Java 8, there was over 7,000 classes, so extra types that were built into the language that come straight with the standard Java development kit. But in other places, the library may be larger or smaller, but they typically have data structures like enumerations, tuples, arrays, strings, lists, unions, subtypes, and then any other subtypes and function types they're derived therein. And so for each one of these, there's some connection between how sets themselves, like think about the mathematical construct, sets are defined mathematically, and how types are defined in programming languages. There is a deep level connection to that, and this is sort of like this, along with algorithmic theory and discrete mathematics, is the math of computer science. So, making sets by enumeration, right? So we can mathematically construct sets by just listing all the elements, literally just having a set with every possible element that can be in that set listed. Unfortunately, though, when we do that, right, and many languages support enumerated types, right? C, Java, Ada, Pascal, ML, we have the capability to create an enumeration, right? And essentially, these define a new type. This is literally a type where every possible version of, like instance of that type, is literally stated. They also define a collection of named constants of that type, right? So, for example, in the C one, enum coin, penny, nickel, dime, and quarter are the only subtypes or named versions of that type coin that are allowed. In the ML data type day, we have M, TU, W, TH, F, SA, and SU. Those are the only types of days allowed by that data type. So when we want to represent enumerations, right, a common representation is to treat the underlying values, the values of the enumeration as small integers, right? It could be any way you want to look at. Sometimes you don't have a choice, but for example, in the C, right, we can set up the coins to have the value of the actual coin, right, in cents. And so penny is 1 cent, nickel is 5, dime is 10, quarter is 25. But we could also have an enumeration that that's not necessarily showing a number, but rather is using the numerical representation as a character. So these are escaped characters. The typical ones are the alert bell, backspace, tab, new line, a vertical tab, and the return, right? A carriage return. And so, but not all languages that have enumerations allow you to provide this type of value. Some actually will just enumerate them with a sequential value that you cannot adjust. So there are operations that we can do on enumerated values, right? We perform an equality test, right, which checks whether or not, for example, we're looking at a function is weekend, which is defined in ML based on the day data type. And what that's saying is, if X is Saturday or else X is Sunday, then we know that it's one of the weekend days. On the other hand, if we have an integer nature of the representation is exposed, the language allows some or all integer operations, right? So we can do something like in C, where we say int x equals penny plus nickel plus dime, because those are all integer representations, which would then lead us to believe it would be 16 cents, right? Another way we can look at this is by constructing a tuple, right? We can construct sets through tupling, and essentially we can take the Cartesian product of two or more sets, define the Cartesian product of two or more sets defines sets of tuples, where if we have the set S, we're saying that it is the Cartesian product of the set X and Y. It's really saying it is for any pair, any tuple XY, where where X is an element of the set X and Y is a element of the set capital Y, right? So we can use that to as our basis for defining a type. So when we want to represent tuple values, right? A common representation is just to place the elements side by side in memory, right? We take essentially we align sections of memory such that two side by side. If we think of memory as some linear construct, two side by side cells would effectively hold the tuple data, right? But unfortunately, that's very we'll say limited view of what memory actually is. And it leaves out a lot of the underlying details. The question becomes, what order do we put these things in? Are we going to have, so you will have holes in the data, right? The data is would have to fill exactly, the word boundaries in memory, right? And so, how do we get those holes to line elements? Is there is any or all this visible to the program? In other words, do we have the capability as a programmer to really manipulate the memory as and to understand how this is actually being set up, or do we just have a more high-level abstract view of what's going on, and we let the machine take care of everything? For example, in C, right, we can think about this as when you have like a structure, right? Typical structures, for example, arrays or actual structs, have addresses increasing in the order of their declaration, right? So you can actually, if you understand C well enough, you would know this, and you can actually use this to manipulate pointers in order to move back and forth by members using the pointer itself. It's dangerous to do that, but it's very powerful. Unfortunately, in other higher level languages like Java or C# or Ruby even, we don't have this capability. We cannot directly interact with the memory, which has actually been shown to be a good thing. But anyway, just something to be aware of. There are operations on tuple values, right? We can, and this goes back to the in ML, right? For instance, we have the sharp number that gives us the capability to select an element from within a tuple. In C, whenever we're operating on like a struct or a union, we can actually use the dot notation to find the different elements. Other operations depend on how much of the representation is exposed, right? So as I was talking about, if we have in C, if we have a double named Y that really is a pointer to a pointer within the address X, right? And we have a struct person that has some string first name, some string last name, and then P1, which is an instance of the person, whereas the first name is Marcia and the last name is Brady. We have the ability to essentially walk across this using the pointers. Now, another way we can do this is by using vectors, right? So we can create fixed size vectors where basically we have some set X, which is the vector, the nth order vector X, right? Such that X elements X1 through Xn, right? This is are a member of for each I in X sub I is an element of the actual set X, so or the vector X. So when we want to look at arbitrary sized vectors, right, S is equal to X star, where X star is really the union across all possible X ith order X's. So it's the union of all of these, right? That gives us the capability to define the vector, the set of all vectors. Interesting as that is, there are other types that are related to vectors, right? When we're looking inside, so we've seen structs, we've seen enums, right? These are basic types, but we also have types that are related to vectors, which we use all the time. Strings are an array of, are a vector of characters. A list is just a vector of items. An array is a vector of items. They're very similar to tuples, but unfortunately, we can do much more with them, right? And they have a lot of different variation. So typically, also, that vectors tend to be a single type, whereas tuples could be multiple types. If we think about like a struct, which is a tuple, you can have in the one that we saw for C, you had 2 strings in there, but in reality we could probably put in whatever we want, including another struct. So the question becomes, when we look at vectors, like how do we index them, right? What are the index values? Well, they could actually be, they don't have to be numbers. They could be some other data type, like a string. That leads us to talking about hashes and things like that, or dictionaries. Is the array size fixed at compile time? In other words, can we not change it again? Is there a way that we can what can we do to adjust this? For example, in Ruby and Python, our array types or list types have the ability to dynamically be allocated. But if you look at C and Java, once the index value is, once the array size is set, it is set. We cannot go and adjust it without redefining it. Indexes typically in most languages today, they start at 0, but they can, and they're typically indexed with numbers, although there are languages that allow for associative arrays, which are indexed by typically some other object like a string. They're not necessarily dictionaries, though. They're an actual array type. So we get back to these index values, right? As I was talking about, in Java, C, C++, right, the first element of array is the array index 0, right? Indexes are always integers starting from 0. But there are languages like Pascal, which are more flexible, where they actually have, the index types are, various index types are possible. Like I said, integers, characters, enumeration, subranges. This is what we call an associative array. Starting index is chosen by the programmer, so it does not have to be 0. It could be whatever you want, and the interesting thing is the ending index 2 can be it can be selected by the programmer, and the size is fixed, but the size is fixed at compile time. So that means that if you select, for example, let's say you chose to use numbers and you selected the index to start at 5, and that the end index is 10, that does limit you down to a size 5 array, right? It's just that your indexes are possibly more useful to you as in the context or domain in which you're working. So, for example, we have this Pascal, to kind of make this a little more coherent. We have a thing called letter count, right? So it creates an array of integers, which are indexed by the range A to Z. And so what this is going to do is we're going to create a variable counts, right, which is a letter count. And what we're going to do is of type letter count, and then what we're going to do is for each letter that we encounter of that type, we're going to be able to use the actual character, and we can upgrade that. Initially, we want to set each one to maybe 1 or 0, and then as we encounter it, for whatever the case may be, we will increment as we go. Other types related to vectors, there's many variations on the vector-related types. As we already talked about, we always have to ask, what are the index values? Is the fixed at compile time, part or static type, right? What operations are supported? This is an interesting question. Can we redimension at runtime? In other words, so this is beyond just the simple concept of a single-dimensional array. What if we wanted to turn it into a multi-dimensional array? What if we have 6 elements in a single dimension as a one-dimensional array? Maybe we want to turn that into two-dimensional array with 2 columns and 3 rows, or 2 rows and 3 columns, or whatever we want to do. Is that possible for us to do that, or not? Is a higher dimensional array the same as an array of arrays, or is it an entire different structure in memory? Typical approaches, like in Java, C, they're considered to be basically an array of arrays, right? What is the order of elements in memory? How are they structured? Can we access that? Is there a separate type for strings, right? It's not just, Is it its own type, like in Java, it's its own class, or is it simply an array of characters? Can it and if it is its own class, does it handle multiple different encoding types? Is there a special type for lists by itself, or are they arrays? What's the deal? So these are questions that we always have to ask. So now we're talking about, then this is the other one, making sets by union. So this is a question: can we make a new set by taking the union of existing sets? So, union says that if we have some set X and some set Y, the union of X and Y would be all those, it's essentially all the elements in X and all the elements in Y, discarding, only incorporating, because it's a set, once the shared items. And so that's a difficult question, right? So many languages do support union types. For example, C allows a union, and ML's data type is a union, right? And the interesting thing about unions in C is that a union can only be one of the possible internal types, right? So if we say union element, it can be either the integer I or the float f, but it cannot be both. So when we think about that, that means that also that the amount of space it takes up in memory is the largest of any one element, right? So it's the largest space requirements for any one element within the union. When we want to represent these, you don't have the two representations will overlap each other in memory, right? So if we have a union of an integer and a character pointer, it's going to actually create an overlap, right? And it's going to basically selecting the size of the union, as I just said, will be the max of the size of I or P, right? And so the interesting problem is this representation may or may not be exposed to the programmer. So if we have the ability to do this, how much is exposed to the programmer is a question of the actual language you're working in. There's other types, strictly typed unions in ML. All you can do with the union is basically extract its contents. So you can create these things, but you have to say what you want to do with each type in the union, right? So, for example, if I create the data type element that has an I of int and an f of real, if I try to execute this, I have to create a function that can handle both possibilities. So if I say get real f of x, fx equals x, right? I also have to create get real I x equals real x, right? So it has to actually convert. So that's the interesting problem here, is if you do this, you have to make sure that you handle both, or all. On the other hand, there are loosely typed unions, which is like in C, right? These languages expose the details of union implementation. Programs can take advantage of the fact that a specific type of value is lost. So we have a union element, right? Int I and float f, right? If I create a union element e dot I equals 100 and float x equals e dot f, that gives us the we can actually force that to give us the actual value type, but it's going to also include whatever else was in that memory location. So we may actually lose some stuff there. But anyway, what C says about this is that essentially a union may be thought of as a structure a structure all of whose members begin at the offset 0 and whose size is sufficient to contain any of its members, which I was talking about. Basically, it takes the maximum size and uses that, right? At most, one member can be stored in a union at any time. If a pointer to a union is cast the type of a pointer to a member, the result refers to that member, right? So, in general, a member of a union cannot be inspected unless the value of the union has been assigned using the same member. So that's an interesting issue. I've always found using unions in C was a dangerous game at best, but that's my opinion, not to be kept as anyone else's. Middle way would be what we call variant records, right? So this is kind of in between a union and some other types. So union where a specific type is linked to the value of a field, right? Or we can call it a discriminated union. A variety of languages, including Ada and modula 2 use this type of concept. So ADA record, right? Just basically it's showing us that we have a type peripheral, right, that takes in a unit, which is of type device. And then basically we create this record, and what the record has is as like an integer called hours working, and then there's a case which discriminates based on whether or not the unit is a printer or a disk, right? And it says if it's a printer, then the line count is integer. Otherwise, if it's a disk, then it has a cylinder and a track, both integers. And so depending on what kind of device you give it is what type of actual record that it will be storing. We can also deal with subsets, right? So we can define the subset selected by any predicate P, right? So a predicate is simply a logical construct that allows resolves as true or false. So we can say that any that X is a member. So little x is a member of the set X. So we create a set S, a subset basically of X. Which includes any element x of set X, where the predicate P of X is true. So that's what the set is comprised of. And so we can use this same concept. Subsetting creates subtypes, right? Languages support subtypes with more or less generality. The less general would be something like Pascal subranges, which are basically of like type int. But they are limited from the size, so int can be anything within the range of the minimum to the maximum, but then we reduce it in size when we do a range to only this one subset. And so for the case of digit would be 0 to 9. More general would be ADA type subsets, which we can say subtype or subtypes, which is like digit is an integer in range 0 to 9. Subtype weekday is a day, but has the range Monday through Friday. You can have more general concepts, list types with predicates, right? So essentially we create a type, but it's a subtype through the predicate action. So we return back to the ADA subtypes, and now we're looking at the same concept. We have a device, we have a printer and disk. We create a new type, peripheral, that takes in a type of device, which is a unit. Right, then it has the whole record going on. We can then subtype and create disk unit is a peripheral of it. So a disk unit is a peripheral of disk, right? We could then use that in place of which is and then saying that it's only looking at a peripheral that responds to disks. So on the other hand, in Lisp, right, we have types that are with predicates, so we can declare a new type. We have type integer x, right? We can then declare a type with the predicate or null cons. So null or cons x, right? And we can then further declare a whole bunch of other ones. Basically, we're just saying that what's going on here is we can define and refine types using these predicates. Representing these subtype values, usually we just use the same representation for subtypes as we did for the supertype, but we have the ability, if we can access deeper level constructs, we can actually reduce this, right? So and what we're trying to do is make it more efficient in memory. And so the question becomes, do we want to try to shorten it if we can? So for example, we ask ourselves the question, if we have a range of 1 to 9 that is an integer range, right? Does it take the same space as an actual integer? Well, that's a good question, but and furthermore, do we enforce subtyping? So for example, if we say we have this integer type x and it's range 1 to 9, we ask ourselves, is it possible to have one that is 10, or would that throw an error? And what about operation of x? Can we do an assignment to x of x plus 1? So in other words, what operations are available? So these are questions that we always have to ask ourselves. Obviously, if I was defining this type and it was a range, I would not allow anything to go outside the range. I would allow operations, but if the operation effectively caused it to go out of the range, then no, that would be an illegal operation. So that leads you into other things. But operations and subtype values usually supports typical subtypes. Typically support the all the same operations that are supported on the supertype. But it also possibly adds additional operations that would not make sense on the supertype. For example, 2-digit on character. There's an important meditation here. A subtype is a subset of values, but it can support a superset of operations. So I'm going to let you contemplate that and what it actually means and the depth of that meaning while you do that. And then finally, not finally, but a word about classes, right? So the key, as we all should know, classes are a key idea of object-oriented programming. In class-based object-oriented languages like Java, a class can be a type. It's meaning here in object-oriented, it's both the data and the operations on that data bundled together. A subclass is a subtype. It includes a subset of the objects, but supports a superset of the operations. And so the question is, why is that? Well, obviously, we have to understand that it's not a subtype in that it's a restriction on what's going on. It's actually a refinement and expansion of the supertype. And that's why it can support a superset of the operations. So, but we'll talk more about that when we talk about object orientation. And finally, we can also make sets of functions, right? So if we can define a set of functions with a given domain and range, right? So if we recall from discrete mathematics and possibly chapter 0 of the Sipser book for computability, we think about how we can define some function S. S is a mapping between the domain and the range, D and R, right? From D to R. And there's many different ways to define functions, but essentially we are saying that for S is actually equal to the set such that that contains F, such that the domain of F is equal to D and the range of F is equal to R. So that's what we're actually are. So S here would include any function that meets those requirements. So if we want to make types of functions, most languages support some notion of the type of a function, right? So a function, for example, in this case, would be the domain is a pair of characters, and the range here is an int, right? So and the mapping is that it returns the test whether or not A is equal to B, right? In C, an integer is the return value, right? It's either a 1 or some other non-zero number or 0. On the other hand, if we were to write this in ML, it would be the mapping of character by character times character, right? The tuple, character times character, which mapped to a Boolean, right? To a true or false value. So operations on function values, of course, we need to. One of the things we can do is we can call function, right? We've taken for granted that other types of values can be passed as parameters bound to variables and so on. We can't take that for granted with function values. Many languages support nothing beyond a function call, right? Java only, well, up until recently, only supported function calls. But there are other languages. For example, in C, we can actually use pointers to functions, so we can pass them, but as variables themselves. Other languages like Lisp and things like that consider functions to be first-class entities. Haskell does that, and then in ML we'll actually see that. Okay, so that ends the first half of this talk, and so we'll come back to talk about the uses for types shortly here.